If you're working with quantitative data in two variables and the scatter plot shows a linear association between those variables, you might want to fit a line to the scatter plot as best you can. Such a line would be called a best fit line or a least squares regression line for reasons I'll talk about in a little bit. This line could serve as a model of the linear association between your x and y variables. In your scatter plot, if y is the response variable, you should put that on the y-axis and x the explanatory variable on the x-axis. You can also use this line to predict the response. A predicted value of y would be y hat, that has a little hat symbol on top, for some particular value of x. Here's a picture we can work from, and it's just a simple scatter plot, and it's not even really linear, but we'll suppose that these are just 3 points that have been taken out of a scatter plot of many, and we can fit a line to these points, but whatever line we put in, our picture is not going to be able to hit all 3 points simultaneously because the 3 points are not collinear. But we'll do the best we can. We're going to have to compromise to some extent. And suppose we put in a line maybe like so, and try to pass through the scatter plot as closely as we can. We're still going to miss somewhat, though. Right here, there's a little bit of a difference between the value of y out at this point and the value directly below it on the line. And here this point is below the line, here this point is above the line. So there's a little bit of error in this line right here. But this line could represent a predicted relationship. We call it y hat equals a plus bx, where y hat is the predicted or estimated value of y. Okay, and this relationship is a linear relationship between predicted values or estimated values of y and actual values of x. Now, we have two coefficients in this line right here. This a right here represents the value of y hat when x is 0. When x is 0, that term goes away and y is just equal to a. That means a is the y-intercept of the graph of the line. And then b would indicate how much y hat increases every time x increases by 1 unit. So if we were at some point on the line and we were to go 1 unit to the right, we would have to go b units to get back to the line. So that is the slope right there, b. Now if we look at these 3 points right here, for a particular value of x, well, we'll call this value, say, x1. There's a difference between the observed value of y, which is here, and the predicted value of y on the line. And that difference, we call that y1 minus y1 hat, is what we call a residual for that point. And it's just kind of like a little error between what we observe and what the line predicts for that particular value of x. And that's what we call a residual. It's the difference between the observed and the predicted values of y for that value of x. And in this case, that residual is positive because the actual or observed value is above the line. We could make another residual over here for this point. For this value of x, x2, the observed value of y is below the predicted value of y on the line. The residual is y2 minus y2 hat. And this residual would be negative because y2 is less than y2 hat. We can do the same thing for this third point. The value of x at that point is x3. The value of y at this point, the observed value, is y3. And the difference between y3 and y3 hat right here is the residual for that point in our scatter plot. Okay, so what we've got here is we've got some points in the scatter plot. We drew a line through the scatter plot, and every point has some kind of residual. It might be a positive residual or a negative residual, or in some cases, if the point is on the line, it would be a 0 residual. That can happen. But the point is, what we want to do is try to somehow minimize all of these residuals. We want to make, in some way, we want to be able to minimize either the total amount of all the residuals or the total amount of deviation from the line, whether we measure it as a positive deviation or a negative deviation. Somehow we want to minimize that and make the line fit the data as best we can. So in general, what we have for any point, for any xi, the residual for that observation would be yi minus yi hat. It's the observed value of y minus the predicted value of y for that particular observation. And that is the key to figuring out how a best fit line is going to work. Now we have the right to choose which values we want to use for the y-intercept A and the slope B to make the line fit the data in the best way according to some criterion. Now we can choose what criterion we want to follow, but historically the one that has survived the best in the intellectual marketplace for the last 200 years is the so-called least squares criterion, and that says choose values of A and B in the way that minimizes the sum of the squared residuals. So here is a residual, we square it, and then we add up all the residuals for all the points in our scatter plot, and then we try to minimize that quantity. Okay, well this is basically an optimization problem which you can solve with calculus, and that's beyond the scope of this video, but suffice it to say, if you were to apply the methods of calculus to try to find values of A and B that minimize this particular quantity, the sum of the squared residuals, this is where you would wind up. The values of A and B that meet this criterion are B is equal to R, the correlation between x and y, times the standard deviation of y divided by the standard deviation of x. And A, the y-intercept of our line, is equal to y bar, the mean of y, minus B times x bar, the mean of x. Now you can see in these two formulas right here, it clearly matters which variable is y and which variable is x. The response variable has to be your y, the explanatory variable has to be your x, and it matters because if you had interchanged your x's and y's here and here, you get a different value for b. If you interchange your x's and y's here, you get a different value for a. So what values you get for a and b are dependent on which variable is the response variable and which variable is the explanatory variable. Okay? Now, what does the slope mean? Well, in general, slope is a rate of change. It tells you how much a y value on a line changes in response to a unit change in x. So in this situation, we're looking at the slope b. It indicates on average how much predicted y or y hat changes for each unit increase in x. And when you're interpreting a slope, you'll have to use the context of the problem and rely on that to tell you what the units for x and y hat look like and what that relationship might look like. The y-intercept, A, indicates what y hat would be if x were to take a value of 0. In some situations, this is not a very meaningful number. And most of the time when you're studying best fit lines, the slope is the more important of the two numbers that you'd be interested in. Now, if you calculate a best fit line according to this particular recipe up here, you minimize the sum of the squared residuals and generate these two little formulas for B and A, and you apply those, plugging in values that you get from your data. You get your best fit line or your least squares regression line, and there are three useful facts to know about that line. Number one is the y-intercept and the slope coefficients A and B are not resistant. They are based on means, standard deviations, and a correlation, none of which are resistant. So A and B are not resistant either. The least squares regression line that you generate will pass through the point x bar, y bar. So that point, the mean of x, the mean of y, will be on the line always. And then if you were to take the residuals and add them up without squaring them, the sum of those residuals would be 0. You'd have some positive residuals, they would cancel out some negative residuals, and the net effect, if you add up all the unsquared residuals, is you would get a sum of 0. And in the next video, we'll look at an example of how this works.